Thank you and welcome to my talk. My name is Ahmad Fatoum. I'm a kernel engineer with Pengutronix. We do embedded Linux development. A lot of our more recent projects involve secure boot. So a quick show of hands. Who has had contact with bootloader security? Okay, cool. Embedded bootloader security in particular? Okay. What about experience with either Barebox or U-boot? Okay, great. Who has heard of Barebox? Cool. So it's like the same amount. So there were two talks. You already noticed at least one of them at ELCE 2025 this year. There I talked more about like concrete attacks. I took 4 security issues in both Barebox and U-boot and talked a bit about them. There was another talk by Richard Weinberger, which was also about bootloader security, and these had more examples. Here it's more about the concrete hardening measures that resulted from these issues. We already had the talk by Kobus before about his verified boot chain. I thought so the thing is with secure boot, you can understand multiple things under this name because it's also preoccupied by UEFI secure boot. So I thought with verified boot chain, I can like take a term for this boot chain that's different than from Kobus. But so this verified boot chain is a bit different. It's not like the measured boot chain where you have a TPM and where you write values into it, but instead you have a root of trust inside the chip, temperature resistant, electrically burnable e-fuses. Then that encodes public key, and that public key is used to verify a bootloader. The bootloader itself either calls back into the boot ROM, or it has keys embedded itself, which it used to verify a fit image. The fit image often contains a root hash for the DMVerity root file system, and the DMVerity root file system would contain your application. So that way you have a full verified boot chain spanning all software that you would run on the system optimally. Of course, if you were able to mount an attack on the bootloader, you could disable this verified boot chain. Just to compare to measured boot. So with measured boot, you wouldn't release the key used to decrypt your eventual file system. In this case, if you can't verify the next stage, you would just not continue booting because the hash doesn't match. Some information about Barebox. Barebox started as a U-boot fork 15 years ago with an emphasis on being very similar to the Linux kernel, which allows for porting drivers more easily. It's multi-platform, so there are dev configs that can build a lot of different boards at once in one build. For example, multi-v7 dev config supports more than 100 boards at once. There is a visual file system. It has a RAMFS, a DevFS. There is a file descriptor API, so you can just open your eFuses like you would open in vmem under Linux and do stuff. Commands are often ported from BusyBox, for example. There are opinionated frameworks for the whole redundant boot, fallback boot stuff. So you don't actually need scripting for the common use case, but you can always fall back to scripting. This makes it useful in secure boot scenarios, for example, because you can disable large parts of Barebox and it will still work. And you don't have to like use the shell interpreter for everything. I collected some numbers. Just to put things into context, there have been 3,700 commits to Barebox in the last 2 years from 88 authors. Pengutronix, my employer, employs me and Sasha. We do maintenance for Barebox, so most patches are from Pengutronix, but there were 370 patches from the wider community by 61 authors. I hope that will grow. On the last 2 years, we had 22 monthly release, 1 bug fix release. It was not the only release with a bug, but it was bugs that were a bit more critical. So we decided to release a second release in the same month. Upstream, there are a bit over 300 boards supported. Mostly it's ARM v7 and 8, but you can also run it on x86 in place of systemd boot or grub, for example. And RISC-V, MIPS, and so on. And to give you an idea about the configuration space, there are 1,386 promptable configuration parameters currently. So not everything can be selected at the same time, of course, but a lot of them can. More than half of them can be selected at the same time and deselected at the same time. So there is a large configuration space. And the problem is, how do you secure all of that, especially as verified boot is increasingly becoming the default due to, for example, also regulations. Yeah, what's the pretext? A number of vulnerabilities were reported against the file system in Barebox. Some of them were after an audit. Some of them were after an AI-assisted file system code scan. And here they highlight a general issue, which is security collaboration is difficult, especially in the bootloader context, because it depends on every individual use case, what your threat model is to define what's secure. So for one, what is secure for someone might not be secure enough for somebody else. And you can easily shift the blame onto misconfiguration by the user. So if something doesn't work out nicely, yeah, you shouldn't have configured this in. Why do you need a file system? Just use raw partitions, so for example. This is not unique to Barebox. Everybody puts their pants on one leg at a time. But yeah, the question was, what could Barebox do better? Which is what this talk is about. Here is a short example of the file system issue. There were a lot of CVEs about these file system issues. Basically, they were code ported from the Linux kernel. They were fixed in the Linux kernel once bugs were found. But in the bootloaders, these fixes did not propagate. And yeah, this resulted in CVEs when people noticed that we still had this vulnerable code. If you were to actually talk to developers from both bootloaders, they would recommend not using file systems at all. But how would you find out about that without like looking into mailing lists and asking and so on? And this brings me to the first hardening measure, so to speak, which is a new security documentation. So for one thing, we didn't have a disclosure process. People asked it on IRC, then we told them, yeah, here's this email, send an email here. Now we have actually a disclosure process, a security MD file. GitHub even displays it specially. And you know that you can write emails to security at Pengutronix. Security at Barebox. Sorry about that. And security consideration chapter was also something I added because I wanted to help put issues in context. So security researchers reporting these issues, they are not necessarily users of Barebox. And while these issues were critical in the file system, if you already have like a Barebox environment with init scripts that is sourced automatically on boot, you wouldn't go for the buffer overflow. You would just put a shell script in the Barebox environment. So I wanted to enrich the CVEs when they are published with the information when does this actually affect you. And while writing that, I noticed, yeah, we should really write that down. And that's the security consideration chapter that's now part of the official Barebox documentation. It's, for example, tells you avoid use of file system and tells you why, and also tells you what you should be doing instead. Of course, this is only one part. Another part is how can we make it easier to like automate this, and could we have better tooling for that? And I have been thinking about that for a long while, really. When I was young, I asked, why can't we have a config secure? And I was quickly shut down. Yeah, people would enable it and expect the system to be secure. It doesn't work like that. And everybody's secure is different, of course. But now I am older and wiser, and I know I can get config insecure in. So there is a config insecure now in Barebox. When you enable that, you get some convenient defaults, like if you have a GPT partition type UUID, for the Barebox, you have a Barebox environment partition with the correct type UUID, it will just load it. That's very convenient. But of course, in a secure boot system, you don't want that. So you can just disable config insecure and miss out on this feature. But most stuff is not as black and white, so it depends on your use case if it's secure or not. For the kernel, you have, so for example, this kernel config security checker. For Barebox, we have now has insecure defaults, which is an invisible symbol that's selected by options where you should probably take a second look if you really want it. For example, mutable environment, being able to load init scripts from outside Barebox is often sometimes you don't want. But sometimes you have like crypto tokens that unlocks this feature so that it can make sense. But so you actually know that you need to look at it. You have this has insecure defaults that you can look. It will show you what selects it. And every one of these options actually has a help text that tells you why this might not be a good idea for you to enable. And the idea with that is that we nudge deployments into using the security sensitive subset from Barebox, where we are currently looking into hardening it, and over time we intend to expand this subset. But if you have so much configuration space, you need to start somewhere. And this brings me to the next topic: what parts of Barebox are most security sensitive? So what happens before you actually can verify an image? For one thing, it's factory data in EEPROM. This might be SPD on your DRAM stick, but it also might be the type of hardware which is used like as index into an array to know which device tree to use or which RAM parameters to take. There is file type detection. So for example, if you mount a file system, you can just say mount and Barebox will try to guess what kind it is and invokes the correct file system. Or if you have a partition table, it can be MBR, it can be GPT. It's also done over this file type detection. And partition tables themselves, of course, the boot state. So if you want to count how many times you boot, then the actual flattened image tree, which is the signed format where the kernel is in, and sometimes even over the wire protocols like USB. And all of that should be a prime opportunity for fuzzing. And yeah, this was not as easy initially as I hoped, because you need to do a lot of initialization before you can actually start fuzzing. So libfuzzer, it's called lib at the start, but it's more like a framework. It expects to define its own main, and you just implement the function that takes the inputs repeatedly. But that doesn't mesh well with the way you write a bare metal software, which does a lot of initialization before even coming to the point where you can actually fuzz stuff. An example is fit images can have compressed sub-images, and these compressed sub-images do not have metadata how big the image will be when you uncompress them. So it's difficult to allocate space up front. And what Barebox does is the way it needs the least amount of code, which is it opens a file descriptor and it just writes into the file descriptor. The file descriptor is backed by ramfs. So it basically opens a file in /temp and just keeps extracting into it. But that means before you can start fuzzing, you need to set up virtual file system and mount a ramfs. And yeah, so this needed quite a bit of work to get going, but it's now there, it's now upstream, and you can actually run this fuzzing now. It runs under Linux normally. That's this Arch sandbox. It's a normal Linux application. And then you can enable ASAN, undefined behavior sanitizer, stack protector, fortify, and so on, and actually try to find crashes and hangs inside Barebox or memory safety issues in general, and get to fixing them. I wrote fuzzers for some of the critical parsers. So for file type, JSON Web Tokens, fit, device tree, partitions, there are now upstream fuzz tests for that. I ran them and yeah, found dozens of memory issues. And yeah, we fixed those. And what I also hope to achieve with all of this is to make it easy to add neo fuzz test, because most users of Barebox are actually out of tree. Most vendors do not upstream the board code. So the board codes in Barebox, there are some which are real products, but most of it are like evaluation kits or system on modules that are inserted as part of a bigger product. And yeah, you have hundreds, possibly thousands of board support outside Barebox, and they also do their own parsing, and that wouldn't be fast. So I wanted to make it as easy as possible to use. And yeah, that's how it looks like now. You have these harnesses, for example, fuzz test, where you just pass a function that takes data and size, and yeah, you are supposed to like just feed it into your parser. So there is fuzz-test RAM disk for codes that uses open, close, read, write kind of functions. It gets a RAM disk and just operates on that. So there's fuzz-test str for null-terminated strings. And yeah, I would hope that this finds adoption even if I don't see it in out-of-tree board code, because yeah, that's also attackable. Yeah, and at the end are the commands that are used for that. I think the usual way how hard fuzz testing is in a bootloader when it was not written like a library where you can just take single functions out and fuzz them is also the reason that the adoption is not good. So I did a survey and checked what other bootloaders are actually fuzzing. So mostly it's either a proof of concept. For core boot, it's a single fuzz test for JPEG boot splashes. For U-boot, it's a single fuzz test for, what was it, for VET.io rings. For trusted firmware, there is no fuzz testing at all for the bootloader part, just for secure monitor calls. So yeah, for grub, it was never merged. Of course, people do fuzzing, but it's outside, and it's not done on a continuous manner, and issues that happen between the research papers are going unnoticed. So yeah, it was dear to me that this goes upstream and it's easy to extend. And I think, yeah, that's good. That's a good first step. And yeah, in the future, I would look forward to extend it to like USB and MMC and other hardware protocols, because that could also be an attack vector against the bootloader. Yeah, next step, hardening. Yeah, so the status quo is not great. Everything is in the same address base. It's mapped one-to-one, and everything is read, write, execute. So it's like software in the 90s. But yeah, we have, since this month's release, it's 2 days old, we have actually not only protection that read-only memory is read-only, but also writable memory is no longer executable. Yeah, so we have arrived in the 2005 now. Stack overflow protection. Yeah, I want to add something about WXOR-X. It's enabled by default now. I am curious to see what breaks, because of course, you can have codes where you have like a const pointer and the const is casted away, and it usually worked because read-only data was not read-only. Now it's read-only. Yeah, in U-boot, it was enabled in the last month's release, but they opted to not enable it by default. So it would be interesting to see, like, in 1 or 2 years, how did that fare? How long did it take for adoption when you don't enable a security feature by default, or if you enable it by default? Unfortunately, you can't, like, plot user satisfaction. That would be interesting to see. User satisfaction and actual adoption. Yeah, Stack Overflow protection. We have double the hardware random number generator drivers now in Barebox that we had a year ago. This is useful to randomize canaries. This is not enabled by default because not every platform has a hardware random number generator, and it's difficult to get hardware random generated numbers so early in the boot process. But at least stack guard pages are now enabled by default, because the stack actually overflowed into the page tables, which is like the worst place you could possibly overflow into. Yeah, the page tables are still read-write, even if we could switch them read-only now. I guess that will follow in the near future. The problem is we actually do memory mapping at runtime, uncached and write combined for like frame buffers and stuff. So yeah, we would need to switch between them, but I think that should be easily doable. It's just that no one has done it so far. There is some hardening for zeroing uninitialized variables, but I had done no tests to see how much it affects the size of the binary and the performance. So this is not enabled by default, but it's there if someone wants to use it. It was very easy to integrate because it's just GCC options. And yeah, there's a lot more to control flow integrity, not to speak of like additions to the ARM ISA, which doesn't have silicon yet. There is still a lot to do. There is still 20 years to catch up with, but I think this is an okay start. Yeah, and and while we wait for catching up, even when we do, we should slim down the TCB as much as possible, and I think we are on a good way there now. So Barebox contains two components. One is the pre-bootloader. This is a very board-specific part that actually initializes your memory and then uncompresses Barebox to the end of RAM. So the SDRAM is usually a different component, and you need to initialize actually the DRAM with timings and so on. And the pre-bootloader is very, very minimal. It doesn't do like public key cryptography or something. It has just the hash of the second stage embedded. So it does only initialize RAM, read Barebox, check the hash, jump to it. And on ARM v8, it also installs the critical system firmware. So it installs the secure monitor at the highest privilege level. The secure monitor would install Opti, or Barebox loads Opti first, and that's also at a higher privilege level. And then execution returns to Barebox at exception level 2 or exception level 1. And at the same exception level, Linux or KVM will run on. But if you mount an attack, you usually would mount it against Barebox proper, which has all this code that you would call Barebox. And then at worst, you can compromise Linux, but you can't compromise a secure monitor or compromise Opti. So your keys should be secure. We used to do something called late Opti loading. So we loaded Opti just before jumping into the kernel. This is deprecated now. It was only for ARM32. We hope to remove it in a few years, because it's not a good idea to run too long at the highest privilege level. Yeah, and this brings me to the final part of my talk, which is access control. So you don't have like different users in the bootloader. You just need to boot, and with everything being in the same address space and no system calls, everything calls everything. It's very difficult to like establish an access control scheme. So what we had so far was very, very ad hoc. And the same issue remains. Every individual threat model defines what's secure. So you can just say, oh, make it secure, please, at runtime, and then it's secure, because it depends on each individual project. And to actually enforce a policy, this went very, very deeply into the bootloader guts. So you had like very custom functions that, for example, force signed images to be the only thing possible. Normally you would configure this at compile time. But if you have a setup where a developer needs to unlock a device for development, for example, or for field return, you would want the bootloader to support both modes, with signed images and without signed images. So you need a function to switch between them. Similarly, if you have a console, you might want it closed, you might want to open it. And you can do all of that. There is API for that, but you need to know what API. And those that use this never upstream this code, because it's their security critical board code, and they usually don't upstream the board code anyway. So I would say upstream the security critical board code. And yeah, that's not a nice situation. And I hope to introduce it by some access control mechanisms that I call security policies. So the way it works, you can run a new make target. It's called security alt config. There is also security menu config. So there's all these make targets you know for configs, for kconfig. And for example, security menu config, it opens you this cursor application that you see at the right side, and it only asks you security relevant questions. For example, do you want to allow console input? Do you want to execute shell scripts? And it doesn't ask you stuff that it knows can't happen. So if you don't have both console input and execution of shell script, you can't have interactive shell. So it doesn't bother to ask you about interactive shell. So, or if you don't have USB, it won't bother to ask you, do you want to allow fastboot, which is a USB gadget from Android. So it only asks you what's really relevant to the system you have. And in the end, you get these files, devel sconfig, factory sconfig, logdown sconfig. You can name them like you want. You specify them beforehand, fill them out. Each one of them will have a file in the kconfig format. These are all booleans, all options are booleans, and it has a name. And these are normalized by kconfig. And in the end, they are all linked into Barebox. So Barebox has these security policies there. And it's possible to set a default policy at compile time. And that would be the policy that Barebox would use by default. But and if you don't set one, and still there is code that tries to check what does the security policy say, the system triggers a panic. So there is a permissive mode, but you would only use this for development. Normally, you should always have as a policy selected. And the real power is that board code can decide which active policy to use. So you do at compile time determine what security states the bootloader should be in. And then you write the board code that activates one of these predefined security states where you also specified what they should do. And then separate code can enforce this decision. And this gives you this separation between the policy, which can now come from the board vendor, and the mechanism, which can be upstreamed into Barebox. This is an example of how that looks like. So the getChar function gets you a character. Often you don't want any interactive input in your lockdown system. So there is now a macro for that is allowed. This will look up in the currently active policy whether console input is allowed. And if not, it will return an error. Otherwise, it continues. So you can clearly see here there is no way getChar could return a correct value if the security policy says, don't have console input. And this is invasive by design. So the way I showed before with this lots of different API functions, they tried to do stuff at the end. So they tried to like close off all ways you could go to getChar, but now you can, in getChar itself, just checks the security policy and enforce stuff. And that's useful when you're doing updates, that there are not new features added that might compromise your system, because it's easier to secure stuff right there at the source. And yeah, here is an example of how selecting a policy looks like. You can check a lot of stuff to decide which policy is the correct one. You can check if uses JSON Web Tokens, signed JSON Web Tokens. You can ask a trusted execution environment running in your secure world. Or in this case, you could also like ask the boot ROM, am I in a secure booting state? And then in the end, you select one policy or the other just by name. And yeah, this is quite an improvement, I think, about the way we used to do stuff before, because we can now actually upstream the mechanism stuff into the bootloader, and different projects can actually collaborate on it instead of everybody like having hundreds of lines of custom code where they go deep into the bootloader guts to affect stuff. Yeah, so these configs for config files are in text format. They can have dependencies on each other and on the build system. And completeness is enforced. So if you update Barebox and a new security options is added newly, or you change your build configuration, for example, to enable USB, and then you need to decide what to do about USB gadget, the build will fail. So you must decide what you want to do. And because the build fails, you will want to check in this into some version control. And that way you have like a paper trail of decisions where you changed your security policy, which hopefully you could in future get back to and see, okay, after this update, the build failed and these options were enabled and disabled, hopefully with a reasoning why this happened. And that's also better than board code, where it was not easy to see how stuff changes over time. Yeah, the static analysis is a very story is a very short one, a sad one, unfortunately. We config compile test can now enable 655 options. We have static analyzers in place. Some of them are automatic for the libfuzzer stuff. So libfuzzer is part of LLVM. For the libfuzzer stuff, now with LLVM support added in Barebox, Clang Analyzer is even more convenient to use. And we have right now 692 outstanding potential defects. Someone needs to triage that. but at least CI is adding more all the time. Let's see how. We need some organized way to deal with that. But unfortunately, it's a lot of false positives. Unfortunately. Yeah. So what do I look forward to? Security policies, which I introduced right now, that they go into the October release. I want to apply to Google's OSS fuzz once I have fixed the memory leaks. You might remember the story with file descriptors that you open. Imagine this file descriptor that's opened for uncompression goes to /temp. And this creates a directory entry. And then when you delete the file, it's a negative directory entry. And of course, you wouldn't delete the directory entry cache in the bootloader. So you leak 16 bytes every run. After a few millions of runs, your fuzzer gets killed by the killer. This is not great. This is fixed now. But there are a lot of such issues where it was just not expected that some function will be called millions of times. And yeah, that needs to be sorted out before we can apply for OSS fuzz. Upstream downgrade protection is something in the works that I hope will be there in the next few months instead of everybody doing it themselves. And the mVerity support is apparently coming. So we had these 2 talks this week about bootloader security, and we lamented, there is no mVerity. So don't use file systems because the file systems are bogus or they are ripe with bugs. But just less than 24 hours ago, someone sent an initial series, Tobias Waldekrans, for Infix OS, where he adds device mapper support to Barebox and plans to add the mVerity support in Barebox. So I'm really hyped for that. I was meaning to cut down on my slides, but I was preoccupied with learning how to do word art in LibreOffice. I haven't done that since I was 9, so that took a while. Yeah, there is some other security relevant work. I won't go through it. But yeah, if there is something that's interesting to you, just talk to me or just ask a question. And that's it. Thank you.
Questions?
Thank you. Hi, nice talk. So I noticed that you put in the slides that you use AI for code reviews. So would you like to, tell us more about that? Like, what did you find out? How is AI at code reviewing this kind of code? And aside from that, did you also try some, I don't know, AI augmented fuzzing with your libfuzzer pipeline, or do you want to share more about that?
Yeah, sure. I didn't do anything. Some security researcher from Microsoft used Copilot and found issues in Barebox file systems. He actually looked at a number of bootloaders. He had also reported issues against Grub, against U-boot, and against Barebox. And yeah, so I didn't use AI for any of this. I'm still doing my baby steps with AI. But yeah, the libfuzzer stuff is, I believe, some genetic algorithm where it's informed by coverage to increase the coverage, but there is no fuzziness there. There's no AI there.
Just one last question. So why did you pick libfuzzer instead of, I don't know, AFL++ or something a little bit more custom?
Yeah, so libfuzzer is shipped with LLVM, and that makes integration the most easiest. And I wanted other people to also try it out. And yeah, it's just some extra options when you have the package installed. It's I guess AFL-Fuzz is also shipped in distros, but libfuzzer was very easy to integrate. It's unfortunate that's no longer maintained, but yeah, it's still there in LLVM.
Thank you.
A question.
So you said security needs differ. I tend to agree, but nonetheless, I wonder if I would interpret your general statement towards we might need a complete deep load on bootloaders in order to have something available for really security sensitive systems based on your experience. Can you maybe comment on this? So, I mean, like you said, well, default, you recommend disabling file systems. So, I mean, another option could be remove the file system code. So what's your opinion on this?
What's the difference between disabling the file system and removing it?
If you remove it, nobody for sure will use it.
Ah, you mean remove it out of the source tree?
Yes.
It would make stuff very less inconvenient. So not everybody needs a secure boot chain. And yeah, I don't like it that we can just tell people, yeah, enable this and it will be better. But hopefully with the DM Verity support, you will actually have a migration path, because you could tell people, yes, if you need to use a file system, make sure it's signed beforehand. Here's DM Verity, use it. So I don't use file system on Linux also without DM Verity or DM integrity in it. I don't trust the kernel either, even so it has a lot more of hardening work put into it. I always use DM Verity or DM integrity for file systems.
Yeah, but at the same time, now you again argue for adding even more code, so...
I think DM Verity is a bit different because like file system parsers are very, very complex. And doing stuff on the block layer is less complex.
Yeah, but you can still have wrong offset, stuff like this, so...
Yeah, of course, it's not 100% solution. We will try to fuzz it. We will, we will try to keep more closely to the Linux code for the DM Verity stuff. But I think it's a net improvement over file system. And I also found issues in the fit image parser. Fit image is a very bad format for security relevant stuff. It's a device tree. It's arbitrarily nestable. I found issues in the reserved memory handling. This is something that's part of like a 20-year-old device tree spec thing that has no relevance at all to fit images, but it can still be there. And you usually use just a device tree parser, which can do so much more for fit image parsing. And yeah, so this also invites issues. So it's not like there is a greener side of the lawn. It's all not so good.
Thanks.
Questions? Okay, let's thank the speaker. And we have a break now, and after the break, I think there is like one additional both proposal there. So I'm super bad with vision, but I think it's something related to trusted key rings there. So maybe you can introduce.
Yeah, hi. So I added something about trusted keyrings. I think trusted keyrings are cool. They are an alternative to do the whole TPM stuff in user space, but unfortunately they are not as easy to use. They have no looks, script setup integration, and I would really like that. And yeah, I wondered if there are other peoples who would be interested in seeing trusted keys gain wider adoption, because all these toolings that we have use TPMs out of user space and do not use the kernel infrastructure that we have that doesn't only support TPMs, but also other trust sources. So that's a shame.
Yeah, so whoever is interested to join the both, so that's going to be, I guess, right after the break here. And with the both, our program for today and for the whole Linux Security Summit is going to be over. So thank you very much for everyone for attending, and I guess safe trip everyone back home. Thank you.